it's an extraordinary venue. If you, Richie, how did you set this up? Look at the speakers. It's a really interesting way to look at the problem. And I've enjoyed the whole meeting just because of what he's done. Anyway, what I'll do is I'll go back a step. I will make an attempt to bring back into the picture some chemistry, material science, and let me begin that with the first slide, which lays the problem out and allows you to think about it again. Go back and think about how this whole program could look if you think about it from a material science, chemical point of view. So what I show here in this first slide is a series of little balls. This is the semiconductor matrix where the particles are condensed. On the outside of the matrix is the important part of the story. You see these little orange dots. Little orange dots are molecules. I'll come back later and explain to you what they are and how they function. And what's happening is that the sun hits them, and you can see gas bubbles coming off, and that's water being split into oxygen. So this is one half of an electrochemical cell. And I'll sort of build a story around this and the underlying science. Let me go back, though, and just say a few things at the very beginning about the origin of this problem and why there is significance in what we're doing and how we're approaching it. And it really goes back to this whole notion of look at these lovely chemical reactions, if you're a chemist, water splitting, with tremendous amounts of energy stored with two gaseous products. And the technology for dealing with both of them is perfectly well developed, and we heard a story about that earlier in the day. Not just water splitting, but CO2 reduction to almost any product which will burn. Here's an example of methane. So the thought here is to say, wait a minute, these are chemical processes, we know something about that. What we want to do is go back to where I began. I've got this structure, and on the outside of that, notice I'm blowing up the molecular entity, and we'll see more of that later, and I want to get a panel. And the reason why I want to do that is it goes back to the whole notion of solving this problem. If you could do this on a massive scale, every time you build a PV field, do it twice. Half of the field during the day simply absorbs sunlight and puts it in big tanks called hydrogen and oxygen and burn them in a fuel cell at night. All the technology is done. Can you do that with a high efficiency? If you do, the impact on the energy scene would be extraordinary. So let's go back and think through this problem one more time. Where does it come from? How do you begin to think about doing it this way? And that's what this slide starts to address. It really comes out of work way back in the 70s, 1970s. The whole notion of a very important paper that pointed out if you take titanium dioxide and you shine UV light on it, you get water splitting. You make water go to oxygen. At TiO2. That was the beginning of a thought that then got, for us, leverage was something else that we were doing at that time, way back then. It goes back and just looks at the photophysics, photochemistry of simple complexes. Back in those early days, we didn't really have that much of a background. But we knew a lot about some synthetic chemistry. If you look at the periodic table, those of you who are chemists will appreciate the fact that just below iron, the periodic table, is ruthenium. And ruthenium has some remarkable properties, including a variety of oxidation states, which we need for water oxidation. Point number one. What we found was you could do excitation, make an excited state. We know a lot now about these excited states and what they are. Excitation occurs from the metal out onto one of the ligand pi star orbitals. We know about its lifetime and what it does and how it does it. But the thing that we really were after here is shown at the bottom. And that's the chemical reactivity of the excited state just in a fluid solution. So what we showed was you could put it in solution, great, add a small amount of this pyridinium ion. So this is a pyridinium, two of them stuck together. It diffuses up to the excited state, takes an electron away, and makes ruthenium, well, goes to reduced form. The thing about those two taken together with the thought that TiO2 works, you do UV excitation, and that's fine. But that was limiting only because at that point you use a minimal amount of the sun. What this offered for us was if we combined two features, the way to really go about doing this based on chemical tricks that begin to mimic what happens in photosystem 2, and I'll get to photosystem 2 at the end. So the thought was, okay, so build a device, and the device is going to be built on a semiconductor, in this case TiO2. And the way we'll do this is we'll take, a molecule of that kind. We'll make it fancy. Notice I've got phosphonate groups on the outside. I can put this in an aqueous solution and it sticks on the surface. I'll come back and talk more about that later. But I know I'm going to have two functions. I've got to build something more complicated. I've got to have a light absorber there, but I also need to have a catalyst for water oxidation. One of the best places to look for that is also with ruthenium, with its multiple oxidation states. So that was a thought. If we're going to do it, we have to be careful. TiO2 is okay, but the potential that comes out of the electrode, if you're trying to go to a second electrode and reduce water to hydrogen, it doesn't work. You're off by 0.2 volts. If you're going to do full water splitting, you need to have a second electrode reaction where part of the solar spectrum is absorbed here, part goes through the device, is absorbed at the second electrode. In that case, you complete coverage, and you got enough redox potential to get the job done. So that's the goal. How far can we take this? Let me begin. I'll do this in a step-by-step manner, just pointing out, I laid the problem out, what are the issues that you've got to resolve to actually do this? And so let's do it step by step. The first thing I show here is I take this complex that I just mentioned, but I make it fancier by putting phosphonates on the outside. And here I've put it on this substrate. So here's an optically transparent electrode with little spheres on the outside. This is a compact layer. On the outsides of each of those compact layers is this complex, physically absorbed to the surface. And you can see right through it. If you put it on the surface and look at the photophysics, just by doing transient spectroscopy, what you discover, you do excitation, the first thing you do, absorption is dominated by a transition where electrons go out to the ligand, but with a preservation of spin. That undergoes a rapid interconversion on a femtosecond time scale over to the triplet. And in fact, if you look at the dynamics of this very carefully, it's remarkable. What a great way to start, because even when you get to the singlet, before it undergoes this interconversion, it already injects partially. All the rest of the energy goes to a so-called triplet state. It also injects completely. On that surface, we make an excited state that survives for a microsecond and completely absorbs all of the incident excitation brought into the problem by the chromophore. Part number 1 looks pretty good. Part number 2 says, wait, you've got 2 parts of the problem. You've got to do light absorption, good start. We will later cover more of the spectrum if need be, but at least we can do this with high efficiency. What about the rest of the story? So here I show another molecule. In this case, it's a water oxidation catalyst, and it's as advertised, it's based on ruthenium. If you look at this area, there's some really lovely work in other parts of the periodic table. Ruthenium is a wonderful place to look because of all these oxidation states. I show that here very briefly for those of you with a chemical background. We make these complexes in oxidation state, as you can see, 2. If you look at the structures, and here's a structure, so I got pyridines and bipyridines on the outside, I got the phosphonates, I got to have a water. Because what happens in these cycles is you start water oxidation, fine, and notice an electron comes out at a reasonable potential, goes into the electrode after we do excitation. Ruthenium-2 is formed, that goes to ruthenium-3, but something has happened here that even back then was never properly appreciated. And we actually had to talk about this called proton-coupled electron transfer. The term had never been used before. The water oxidation catalysis story didn't exist, so all this had to be invented. Nice part about this, though, look, you start with a water there, you take away an electron and a proton, and now you make ruthenium-4, that's great. All the protons are gone. Remember, in the net reaction, we got to get rid of 2 electrons per water molecule. 2 electrons have to come from one water, 2 from another. We've started the process to here. It then undergoes a further oxidation to ruthenium-3. These things build up in solution. In some case, with good catalysts, you've got to move really quickly to see them. It then undergoes a reaction with water to make this peroxide intermediate. We can sometimes see these by making variations in the complex. It undergoes a further oxidation to a ruthenium-3 peroxo, and we can see these spectroscopically. That complex in particular survives for a while, but then oxygen comes out, it goes back to the aqua complex. It's done. Water oxidation catalysis. And I'll come back later and use this in these overall schemes. There is an additional problem. As I go through this, as I alluded to in the very beginning, there are a whole series of things that have to be dealt with. And this is number 2 or number 3. What it says is, this is pretty darn good, but if I want to do these experiments in aqueous solution, I want to be able to vary the pH and vary the conditions to control the reactivity. And I can do that by just by using buffers and controlling the pH. If I look at one of these electrodes, and here's the one I just showed you, put it on the surface, that's great. In acidic solution, it's actually relatively stable. It might sit there and last for a couple days. But one of the things I wanted to do was increase the pH, because I know with that complex, from what I know about the water oxidation chemistry that's based on oxidizing the metal, losing protons, if I go to high pHs, I can make this water oxidation really fast by putting a base in the solution because it pulls the protons away from the complex in the rate limiting step. The rate constant for that oxidant under those conditions is 10 to the 6th. That's 10,000 times faster than photosystem 2. So there's no joking around. This is pretty good stuff. But if you put it on the surface and you watch, the next thing you notice, it's gone. It just washes right off the surface, as any organic chemist would have told us. So we have problem number 3, perhaps, to solve. What we did here was to take up atomic layer deposition big time. We have atomic layer deposition machines around us everywhere. Because what we do is we put this thing on the surface, that's fine. And then after we put it on the surface, on a layer by layer basis, using atomic layer deposition, we slowly build up structures around the complex. We can build the structure up just far enough to leave the water exposed to the solution, and it still works. The loss of reactivity is minimal. It's still on the surface, and we can tell. And I would argue, we haven't had a chance to do this. This is a very clever way to take synthetic chemistry, which is, we're trying to take advantage of that, and do something special reactivity-wise, because you can really stabilize the outside. I think we could probably make catalysts that go to hundreds of degrees and control the content in a chemical sense. Anyway, that's good. The other part of the story that we got to make sure that we maintain is, hey, okay, can you build complexes as advertised, and do they behave? So here is a so-called cyclic voltammogram. So I take one of those electrodes like I just showed you and start and apply a potential. And as I increase the potential of the electrode, notice versus a reference that electrode is like normal hydrogen electrode. As we increase the potential, first thing we do is we lose an electron. The assembly loses an electron, it becomes oxidized once. It's good. Go a little further, it's oxidized twice, also good. Go a little further and notice there's a big increase in current. We know what happens there is actually pretty interesting reactivity-wise. An electron comes out, sure, but I now got one ruthenium on the complex and one on the catalyst, and that's enough. It still does water oxidation at a rate far fast enough for us to do water splitting with the sun as our source. So we do have the reactivity we need, so that's another step forward. So let me take a look at this and show you how far we've gotten with the story. I got a complex I advertised from the beginning, put it on the surface, it works. It would sit, and I could use this thing for a couple days. It would still do water oxidation catalysis. That's very encouraging. But there's a big, big problem. We keep coming across problems. This next problem has to do with time scale. Because what happens is light absorption is dominated by that. This is a relatively weak light absorber, so it injects. It takes the electron from the complex with efficiencies on the femtosecond time scale, perfectly fast. That's great. We can build up redox equivalents, and now they get in the semiconductor. Next step, they got to go through all the way through the semiconductor to the inside and then go to the other electrode. Problem is these are semiconductors. Electron transfer is not fast. It takes milliseconds for the electrons to go through the semiconductor. And yet, if you look at this, we got a real problem because the sun is a crummy light, if you're a photochemist, a crummy light absorber. You got to wait and wait and wait for all these photons to build up, and every molecule's got to get oxidized, got to pick up 4 photons. And by that time, Electrons go in. If I look at time scale, electron also can come back out. So it takes milliseconds to go through. It takes microseconds to come back out. The whole thing is collapsed. It can't possibly work. It's dumb. So at that point, you've got to take an additional step. And what we did here, again, was go back and use these surface techniques, in this case, back to the core shell machine, and do something else. So we start with the structure looks like this. Complex is on the outside, as I showed. You do excitation. Electron goes in and diffuses through, but in this case, pops back out. So what we did was take the same structure, but we built a core shell. We put a little thin layer of TiO2 on the outside. 4 angstroms is all it takes. That's all you need. Electrons go into it, and then they very quickly go into the inside, and then they're diffused to the electrode. Depending on how you put that together, you can have a huge impact. And we can get to the point now, I think, where for every photon that gets absorbed on the outside, 50% get all the way through to the inside using these kind of structures. More progress is made. Let me finish this off, though, with a quick summary of where we are in this business and where I think we can go. One observation of note is we've really developed an awful lot of the science. Here, for example, is an organic chromophore, so we're now looking at the spectrum that the molecules absorb systematically. It sits there. If you put these molecules, or organic molecules, you put them on the surface this way, an aqueous solution, and did an oxidation, they would quickly decompose. What we've done now is to bury it in TiO2. The molecules are stable in this environment. But on top of that, then I've got another reagent. This is just an electron transfer mediator. Electrons go quickly from outside, or from the dye on the inside to the outside. And once it gets to the outside, it then slowly oxidizes, in this case, the catalyst. This is a different kind of catalyst from the one I showed before, but it still works. It works very nicely, and we use it a lot. So progress is being made on this front. I would say at this point, I'm mildly optimistic in that I think we can make structures of this kind with efficiencies approaching almost 3% that would last. Remember, this is just for one electrode, not two. It would last almost, well, for hours. So progress has been made. But to finish up, let me just show you some other things. If you're clever about this, there are some promising leads that you can follow up. And a lot of this is just one-time experiments. Graduate student does something smart without, really following up to the extent that we should. But here's an example. If you look at an extension, so here I have here's a chromophore catalyst assembly. Slightly different, but notice I've got that new catalyst on the outside, so I've got kind of a structure of that kind. And I know if I look at this, I'm 0.2 of a volt off, so now I do a combined electrode, put an electrode in the middle where I take the potential off that, and I can do water splitting. Another way to think about this, silicons we've discovered is wonderful stuff. We know a little bit about the underlying physics here. We really admire it. So here's a case. We said, well, wait a minute, let's branch out and think about it a different way. So in this experiment, we take the structure I just showed you. So here I got the complex. I got on the inside of that, this core shell thing on the inside. On top of that, I bury it on a piece of silicon. Now light comes in. Part of the spectrum gets absorbed here. The rest goes to the silicon, which absorbed all the way into the near infrared. That light goes across the other side to make hydrogen. So the whole thing is a water splitting cell. So there are ways to play this, I think, in a clever way. Let me finish, though, with some words about carbon dioxide reduction. And I want to say some things about it in the background underneath the subject matter and make a point. One was I started out talking about the virtues of ruthenium. And here's another example, and I should have emphasized it at the time. Here is a molecule. I could use that as a water oxidation catalyst. In fact, here's an electrochemical cell. If I take that molecule, it is a water oxidation catalyst. It goes on for a couple of days. If I make a cell and I put it on one side of the electrode, that's great, but I can put it on both sides of the electrode and apply a potential. Because one side of the electrode, I do water oxidation. By applying the bias on the other side, I can, at the same time, do CO2 reduction. Same catalyst, both sides. In fact, we can actually make cells where we have this thing surface loaded on both sides. So the chemistry here is very flexible. and approaching a point that's really of some interest. And here are just some data that show you what happens here in bicarbonate. If you look at the ratio of carbon dioxide or CO as a product versus hydrogen, you can adjust that just by varying the reduction potential. Here's a case where we vary the pH, and we also get a variation between CO as a product and hydrogen as a product. But let me finish the story here by saying something slightly different. We're working very hard on the other side, that is the side where water reduction or CO2 reduction would occur. But there's a real problem here. And, you know, I guess I'm learning to enjoy physics and semiconductor physics a little bit. But there are some real problems in this business. For example, if you think about electrodes, the best one that you need, remember what I got to do. I got to put something on the outside. I'm going to do excitation. Then I want to bring electrons out of the electrode. If you think about places that you can really take advantage of this, semiconductor-wise, the best one that you can come across turns out to be nickel oxide. Nickel oxide, you can use it, you can make films, but the dynamics at nickel oxide of electron transfer are horrible. This is awful stuff. So many people have wasted so much time using it as an example. Start out with the same chromophore, but now look at time scale. Here, as you can see, I do excitation. Picosecond time scales later, this stuff, back electron transfer occurs very fast. Before I can get the electrons out, they just undergo back electron transfer. And we've wasted a lot of time. I'm not going to make the point, we're now looking at a couple different semiconductors, and none of this is straightforward to get the energetics right. But I think there's some promise in this area. But let me just finish with something else. And what it says is if you look at this whole business of building assemblies and think about it one more time, so wait a minute. If you look at the photocathode that I just talked about,
It's going to be published in the future.
this, how do you know that? Yes.
106. You're looking at it.
Oh, good Lord, look at that. No. It was published in 2016. 2016. You're right. Gee whiz, I didn't think about it. I missed the point. Anyway, to look at the assembly and the thought process, changing the dates at the top, what we said to ourselves was, well, wait a minute. You know, if I look at this, we really, when we did this and put it all together, we took advantage of the properties of semiconductor surfaces, and we had to build lots of features in. Another way to do this, if you're bright and clever, and I think this might actually work, is to do the whole thing chemically. Don't worry about semiconductors. Just go back to oxide surfaces where I can just put something on the surface, electrons go to the electrode and go somewhere else, period. So we've done a series of experiments that look like this, just to go back to the very beginning, but redo them. So here I got a light absorber, that's great. So photons come in, they see the complex, it undergoes excitation and now transfers electrons through a bridging group to a methyl viologen. Remember, we used that before. And then it undergoes electron transfer to the oxide electrode and it's gone. That leaves the complex oxidized. If I look at it, electrons come from outside in. That gives me an oxidized version out here. Following the excitation, electron is there. I can build up about a volt of potential, and it lasts 5 seconds, 6 seconds. Just by using the chemical tricks of making these assemblies, we can begin to control time scale longer than the sun is in terms of its frequency. Let me just finish here with an example that just shows the kinds of thinking that you can do without thinking about trying to solve the problem broadly generally, but it does go to a point. Here is an assembly of this kind, and notice what you've got. Here's the oxide, I pointed out, everything's built off it. Here I got the methyl viologen, that's good. Complex, now I put in a second complex of iron, and then I put that catalyst on the outside. If you look at that molecule, it's got all the pieces of photosystem too, all lined up in their own peculiar way. So you do excitation there, electrons go that way and out this way, and you can start the process of water oxidation. And it does, it works. May not be the world's best, may be the world's first that does this kind of fancy chemistry. But it just makes the point, I think, if you think about these problems from the chemical point of view, I think there are a lot of interesting things that you can do. Let me just finish, though, with a thought about where all this comes from and why. We have been, at UNC, we were one of the beneficiaries of this Energy Frontier Research Center program. And I think I feel very strongly about the power of the program and the impact it had on training students and doing academic science, certainly at UNC. We put this operation together with the students taking the charge. Faculty were the leaders, sure, but we created a group of people, built a structure around them, and as you can see, catalysis, assemblies, interface dynamics, photocathodes. They, as groups, got together. They, as groups, solved big pieces of all those problems I talked about. We feel very good about what they did and how they did it. The final comment here's a shot from a year or two ago. When I was in London a long time ago, I bought an MG B&T, and I still drive it. So this is sort of a souvenir of the whole operation. Thank you.